Hello everyone, and welcome back to our third session on the GloVe embedding model. In this video, we'll derive the GloVe objective function step by step and then examine the detailed architecture of the model. In the previous lesson, we explored the co-occurrence matrix used in GloVe. Today, we'll build on that foundation to derive the objective function and see how the entire model is organized. So let's begin with the basic idea behind the objective function. Let's revisit the high-level conceptual diagram of the GloVe model from our first video. In this slide, the notation has been adjusted slightly to match the original GloVe paper. Here I represents the target word index, and J represents the context word index. W and W prime are the embedding matrices for the target and context words, respectively. Each matrix has a size of V by M, where V is the vocabulary size, and M is the embedding dimension. WI is the embedding vector for the target word, and W prime J is the embedding vector for the context word. Here, Pij denotes the co-occurrence probability of context word J given target word I. Our goal is to train the model so that the dot product of these two embedding vectors approximates the logarithm of this co-occurrence probability. Let's see what this means geometrically. As the probability P increases, the dot product of the two embedding vectors should also increase. Since P is always a value between 0 and 1, log of P is always negative. Therefore, the dot product is also expected to be negative. As the probability increases, log P increases from a large negative value toward 0. As a result, the dot product also increases. Geometrically, this means that words that frequently occur together are represented by vectors with a larger dot product than words that rarely occur together. One way to interpret this geometrically is that the angle between the two vectors tends to become smaller as the co-occurrence probability increases. Later, we'll introduce the bias terms, which make this geometric interpretation more general. For now, we'll ignore the bias terms and focus only on the relationship between the dot product and log P. Now let's consider the opposite case. What happens when the probability P becomes smaller? As P approaches 0, log P approaches negative infinity, so the dot product also becomes a very large negative value. Intuitively, you can think of this as the angle between the two vectors becoming larger, pushing them farther apart in the embedding space. As a result, words that rarely occur together become less similar to each other. This is the key intuition behind the GloVe model. Now let's translate this intuition into a mathematical loss function. In the co-occurrence matrix, the number of times target word I and context word J appear together is denoted by Xij. If we sum Xij over all context words J, we obtain Xi, which represents the total number of times target word I co-occurs with all context words. Therefore, the conditional co-occurrence probability can be written as Xij divided by Xi. Now let's substitute this probability into our original equation. By applying the logarithm rule, we can rewrite the equation as follows. Notice that the term log xi appears in the equation. This term behaves like a bias term in a linear regression model. Instead of treating it as a fixed value, the authors introduced two trainable bias terms, bi for the target word and b'j for the context word. These bias terms are learned automatically during training. The left-hand side represents the estimated log co-occurrence count, while the right-hand side represents the actual log co-occurrence count, computed from the training data. The difference between these two values is the prediction error. Squaring this error gives us the squared error. Therefore, the objective of GloVe is simply to minimize this squared error. The larger the difference between the estimated and actual log co-occurrence values, the larger the loss becomes. As a result, larger gradients are produced, allowing the model to update the embedding vectors more aggressively during backpropagation. In this sense, GloVe can be viewed as a regression model that predicts the logarithm of co-occurrence counts. However, using a simple squared error introduces two important problems. First, if xij is 0, then log xij is undefined, making the loss impossible to compute. In practice, we simply exclude word pairs with 0 co-occurrence counts when constructing the training dataset. This avoids the implementation issue, but from a mathematical perspective, the loss function is still incomplete. Second, if a word pair has a very small co-occurrence count, such as 1 or 2, its contribution can be dominated by statistical noise. These rare co-occurrences are much more likely to be noise than meaningful statistical patterns. If they produce large prediction errors, the model may overfit to these noisy observations. To address both of these problems, the authors introduced the weighting function fxij. Now let's take a closer look at the weighting function. The weighting function used in GloVe is defined as follows. This function has two hyperparameters, xmax and alpha. In the original paper, the authors recommend setting xmax to 100 and alpha to 3/4. The function is piecewise. When the co-occurrence count xij is less than xmax, the weight is computed using the first equation. Once xij reaches or exceeds xmax, the weight is simply set to 1. Let's see why this design works so well. Consider a word pair that co-occurs only once. In this case, xij is 1, so the weighting function assigns a weight of only about 0.032, which is a very small value. As a result, rare word pairs contribute less to the overall loss, making the model less sensitive to noisy observations. Now consider a word pair that co-occurs 100 times or more. Once the count reaches xmax, the weight becomes 1 and no longer increases. This prevents very frequent word pairs from dominating the loss function. In other words, once a word pair has appeared often enough, additional occurrences provide relatively little new information. This weighting function therefore strikes a balance between rare and frequent word pairs. It reduces the influence of noisy, infrequent co-occurrences while preventing extremely common pairs from overwhelming the learning process. As a result, the model focuses on the most informative statistical relationships in the corpus. The graph on the right illustrates this behavior. The horizontal axis represents the co-occurrence count, and the vertical axis represents the weight assigned by the function. Notice that the weight increases smoothly for small co-occurrence counts and then gradually levels off. Once the count reaches Xmax, the weight remains fixed at 1. This simple weighting strategy is one of the key ideas behind the GloVe model. Now that we've derived the complete objective function, let's see how it fits into the overall GloVe architecture. First, let's take a look at the co-occurrence matrix shown here. This is the co-occurrence matrix we generated in the previous video from our simple corpus using a symmetric context window of size 3. From this matrix, we construct the training dataset. We simply extract all the entries where the co-occurrence count Xij is greater than 0. The target word index I and the context word index j become the input features, while the corresponding co-occurrence count Xij becomes the target value. This forms the training dataset used to train the GloVe model. Next, let's take a look at the architecture of the GloVe model. The model consists of 2 input layers, 2 embedding layers, a dot product operation, 2 bias terms, and the loss function. Now let's follow the data as it flows through the model. The target word index I and the context word index j enter the 2 input layers and are passed to their corresponding embedding layers. The embedding matrix W stores the target word embeddings, while W' stores the context word embeddings. Both embedding matrices have a shape of V by M. From these matrices, we retrieve the embedding vectors Wi for the target word and W'j for the context word. In addition, the model includes 2 bias vectors. The target bias vector is B and the context bias vector is B'. From these bias vectors, we retrieve the corresponding bias terms Bi and B'j, which correspond to Wi and W'j respectively. Finally, the model computes the dot product of Wi and W'j, adds the 2 bias terms, and compares the result with the actual log co-occurrence count computed from the training data to calculate the loss. The gradients are then computed from the loss and backpropagated through the entire network. Using gradient descent, all model parameters are updated, including Wi, W'j, Bi, and B'j. Through this iterative optimization process, the model gradually learns word embeddings that capture the global statistical structure of the corpus. After training is complete, the final word embedding is obtained by summing the target and context embedding vectors. For example, the final embedding for word k is Wk plus W'k. And that's the complete architecture of the GloVe model. In this video, we derived GloVe's objective function and explored the model's detailed architecture. In the next video, we will implement a simple GloVe model from scratch using Keras. Thanks for watching, and I'll see you in the next video.